a neighborhood, and you have a street on which you have the homes, and every home has a street address. So if somebody tells you the exact street number of the home, then you can find your friend's home. And that's the same method we use in computers, say in random access memory, where we have to know the address of a location in memory to be able to find the value stored at that point. So we talked about some value that is stored in memory, say, and if you want to find that value, then you need to know its address, right? So if you were to store an address, so we'll take an example. I'm going to take this out. Yes, not using it. So let's say you had a 4-bit computer. Oh, thank you. And you were to store numbers. So this is the max amount of memory you have on your computer. So how many cells are there on this computer? Can you count and tell me?
16.
16. So on a 4-bit computer, and most of the computers are not 4-bit, right? I mean, like this one is a 32-bit computer. So.
But how do you know it's 4-bit?
How do I know this is 4-bit?
Yeah.
No, I'm just saying on a 4-bit computer, you would be able to store only this much data if you had memory, let's say. And most computers have memory, right? So if you were to store, it's sort of like saying you have a little address book with you, and it's got like only 2 pages. And you have, say, 10 lines per page, and 10 lines for the second page. So that means in this address book, you can only store 20 addresses, let's say. And you had 20 friends, then you're fine. You can store the addresses of all the 20 friends on those 2 pages and you're done with it. But let's say you have 30 friends. Now there is no place to store data. So when we talk about address book as in computers, there's the same limit. So on a 4-bit computer, you would only have like 16 places. So if you were to store some numbers or some information here, you would have a limit on how much data you would store. And you would also be able to uniquely identify every point in this memory simply by using a number or an offset, what we call an offset. So let's take an example. So if you had some name like Joe here, and then maybe you had and something like that. E at the end, I don't know. Okay. So if this was the string that you were looking, or if this was the word you were looking for, all you need to know is the address of this word. And the address in this case can be represented using only 4 bits. That's what I meant. You don't need more than 4 bits to represent this address. Why? Because you're within a 4x4 kind of matrix for your memory. But if, let's say, you had more money, right? And you can buy more memory for your computer. I'm going to take, yeah, that's fine. Just assume, maybe add a few more columns. Make it bigger. Sorry. So this is 1, 2, 3, 4, 5. No, 6. 1, 2, 3, 4, 5, 6. So we have 6 cross 6 now. Except, so you had money to buy this much memory for your computer, but you only had a 4-bit computer. What I mean by a 4-bit computer is the way you count or store information, that information can be stored only in 4 bits. So then you would go, say, 1, 2, 3, so these are 6 rows, right? 6 plus 6, 12, and then 12 plus 4, so go up to here. So I'll just shade this part. So if you were to locate a point on this computer, and if you had your name here, something you're searching for, there's no way to find this address in memory because you only had 4 bits, and the largest number you can store is up to here for the offset. And the way to think about that is you start numbering this. So you just say this is 0, this is 1, this is 2, 3, 4. So these are addresses, not the actual value. The value is something else. So 0, 1, 2, 3, 4, 5. Let's say you had Joe here, right? So we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 0 to 15, you had a 4 cross 4. So you had only so many possible unique addresses. So you are not allowed to have more than that many addresses, which means everything after that is kind of wasted. So, this happened with computers, like in the 90s. They had, people had the money to buy like more memory, but the computer was still 16-bit. So you could only go up to a certain number. After 16 bits, they couldn't actually extend the memory anymore. So that's why it's important for you to know that just because you have more memory on a computer, you cannot necessarily use all of it. You have to know the addressable memory. So the concept here I'm talking about is so why am I talking about this? I'm talking about this is because this will give you an idea as to what role does the number of bits or plays in terms of storage, and how large addressable memory can help you address computers. So in case instead of 4-bit, if you had an 8-bit computer, then you would be able to handle this much memory. And most computers are not 8 bits nowadays, so they are minimum of 32 bits. So most big numbers are taken care of. And one way to know what a 32-bit computer is, you take 2 raised to 32, that's 32-bit computer, in terms of the number of bit possibilities. This will give you 2 raised to 10 into 2 raised to 10 into 2 raised to 10. This is sort of, the same thing. So 10 plus 10 plus 10, 30, 32, right? So you can also say 2 raised to 10 is 1 kilobyte, and 2 raised to 10 into 2 raised to 10 is 1 megabyte. You can say this is 1 kilobyte into 1 kilobyte into 1 kilobyte into 4. And then you can also say 1 kilobyte into 1 kilobyte is nothing but, we learned that it's 1 megabyte, right? So it's 1 megabyte into 1 kilobyte into 4. So this is simple stuff. Not to get too scared of this. This is simple numbers. And this is nothing but 1,000. So that's 1,000 megabytes into 4, or 4,000 megabytes, which is nothing but 4 gigabyte. So what we are saying here is that on a 32-bit computer, the max amount of memory you can address is 4 gigabyte. So if you had more than 4 gigabyte memory, I know this is a 32-bit computer, let's say, okay, maybe it's 64-bit, I think, but let's say it's 32-bit computer. Then if I have 4 gigabyte memory on this, I'm fine. That means I'm able to find every address on the computer within 4 gigabyte. But if I had 8 gigabyte memory on a 32-bit computer, I'm actually wasting the remaining 4 gigabyte. Or if I had 6 gigabyte, remaining 2 gigabyte I would be wasting, because there's no way to find data on those remaining 2 gigabytes. The first 4 gigabytes you can find them, but the last 2 gigabytes, there's no way to address them because you don't have enough space in your slots to actually address those areas of memory. So that's what I talk about. This is a quick way to say that a 32-bit computer has 4 gigabyte of addressable memory. Similarly, nowadays some people like you can take some supercomputers have a lot more memory requirements. So one way to kind of remember is 2 raised to 40 is is a good number to remember. Why is it good? Because it's nothing but 2 raised to 30 into 2 raised to 10. But 2 raised to 30 is 1,000 into 1,000 into 1,000, which is nothing but a billion. So you can say this is a billion, 1 billion into again 1,000, because 2 raised to 10 is 1,000. So this is 1 trillion, or 1 tera. So somebody tells you, I've got a terabyte of memory or something, or usually disk space is terabyte, because terabyte of memory is pretty expensive nowadays. If you want to buy that much memory, you normally need a lot of money, but disk space, it's getting there. Like this one has like 500 gigabyte memory disk. I don't know if you remember in the beginning I said about disk space versus memory. So disk is usually slow speed memory. It's not any different, it's just slow speed. So you can store on a 2 raised to 40 bit, that is a 40-bit computer, and not many computers are 40-bit, but if you were to have terabyte of memory, you can't really have it unless you have a 40-bit computer. But if you have a 64-bit computer, then you're fine. You can pretty much store a lot more than terabyte. Now you know how big is a 64-bit